Hi, I am Junish. I will be presenting TransLIST, a transformer-based linguistically informed Sanskrit tokenizer. This is a joint work with Ratin, Naren, and Professor Suvendru, Professor Behra, Professor Goel. There has been momentous development in digitalization efforts. However, we find its limited usability due to the linguistic challenges. Sanskrit word segmentation conventionally serves the most fundamental predicate for the text processing, and it is useful for downstream application tasks such as text classification, morphological tagging, dependency parsing, and automatic speech recognition. Sanskrit word segmentation is mainly challenging due to Sandhi phenomenon. It is non-trivial because of Sandhi phenomenon, which create phonetic transformation at word boundaries. And these modifications mainly at juncture point by deletion, insertion, and substitution operation. For example, this input, you can find there are various possible solutions, and at the juncture point there are modifications due to the Sandhi phenomena. And key challenges involved in identifying the location of the split and kind of transformation. So in this example, there are 6 possible syntactically valid split, but the task is to find the split which is also semantically valid. There are various approaches taken in literature, mainly rule-based approach, data-driven approach, and lexical-driven approach. Let us briefly review these two approaches. Lexical-driven approaches mainly built on top of shallow parser called Sanskrit Heritage Reader. This shallow parser generates exhaustive space of possible solutions. So here two possible solutions are given. They are colored by different color coding scheme. So this lexical-driven approaches, they formulate the task as finding the most accurate semantically and syntactically valid solution. So here all two syntactically valid solution is there, and the only one solution is semantically valid. So they rely on completeness assumption of the SHR, which is optimistic given that SHR does not use domain-specific lexicon. That means that if this first step becomes failed, then these approaches become handicapped. Coming to the data-driven approaches, so they perform surprisingly well without any explicit handcrafted features, and they are known for their scalability and deployment for training and inference. But drawback of this approach is that they are blind to the latent information even if it is available. To mitigate these shortcomings, we propose a transformer-based linguistically informed Sanskrit tokenizer, also called as TransLIST. There are 3 key components of this module: linguistically informed tokenization, soft mask attention, and path ranking for corrupted prediction. So basically this last module is post-processing module. For list module, we experiment with 2 variants. If SHR space is available, then we use that, and in case SHR is not available, then we rely on the n-grams. So this is our main architecture. This is purely engineering pipeline, which is character level prediction, character level architecture. And here we integrate the information, latent information taken from the SHR, or in its absence the n-grams, they are integrated here. Then second module goes here, which is soft mask attention, and finally post-processing module is used during inference. Let us understand our model with the toy example. Given the input, task is to produce the segmented output. This is the auxiliary information from SHR. So here we are comparing with the state-of-the-art model's prediction. So here bold letters are the incorrect output given by the model, So if you see that without a post-processing module, our model also makes mistake. But with the help of auxiliary information, we are able to rectify that mistake. So this is the overall idea behind the model. So our main contributions are we propose a linguistically informed tokenization module to handle the Sandhi phenomenon, and a novel soft mask attention to add inductive bias for prioritizing potential candidates, novel path ranker to rectify the corrupted predictions, and we achieve the state-of-the-art performance compared to the current state-of-the-art model with average 7.2 points perfect match absolute gain compared to current state-of-the-art model. Our code base and all the data sets are public level available for the future resource. Let us understand each module briefly. Coming to the first module, list. List encodes the character input along with the latent word information. So these are the character inputs and word information is integrated. It takes into account the Sandhi phenomenon specific to the tokenization, and also apt to work with partial or no candidate space. So it's not necessary that we should have a complete candidate space with us. Even partial candidate space is fine. Yeah. And in case we don't have such space, we can use n-grams as a proxy for substitution for this lexical model. Coming to the second model, soft mask attention. So there are two requirements: mutual interdependence between the constraint and inductive bias about prioritizing some constraint over another in low resource setting. So it can be achieved through vanilla attention, but we need more data for learning both things. And if we use hard mask, then we will lose the mutual interdependence. That's why we are opting for soft mask attention, which will help to prioritize some constraints or others by keeping all the mutual interactions intact. Let's understand from example. Let's say we are predicting corresponding output character for this S character. So relevant constraints are only these highlighted two words. If you want to predict for the O, the relevant constraint is only this word highlighted by orange color. If you want to go through more details, so you are free to look into our papers regarding mathematics behind this model. Finally, PRCP is the post correction module. In case the model predicts incorrect word, so we enumerate all the possible solution, and the solution which is having maximum score from our scoring function is labeled as the correct output from our model. We evaluate our system with available benchmark datasets. These are the results. Compared to all strong baselines that we evaluated, our system reports the best performance. Specifically, it shows improved performance on perfect match metric. So it shows considerable improvements in terms of perfect match. We also perform analysis. We investigate various questions to dive deeper into the proposed components and investigate the capabilities of various models. We have performed ablations in two ways. First, in the individual components of the proposed model, and scoring function of the post-processing module. So we can see that each module is essential for the improvement. Later, we also experiment with the possible list variants, and we show that the proposed variant using the SHR shows the improvements compared to counterparts. We also investigate how our model works in non-trivial Sandhi scenarios compared to the current state of the art. So you can see that compared to this, our model outperforms in all the scenario. And robustness on sentence lists. So you can see that our models outperforms the competent baselines, even the sentence list is high. We also perform probing analysis. So there are three components: char, word, and char-word interaction. So strength of the SMA decreases in the following order: red, orange, green, blue. So you can see that corresponding weights of those attentions, and there are interesting patterns. So more details you can look into the paper. Conclusion: to address the shortcomings of existing approaches, we demonstrate the efficacy of TransLIST as a win-win solution. TransLIST induces inductive bias for tokenization in character input sequence using the list model and prioritize the relevant candidates with the help of soft mask attention, a novel path ranking algorithm to rectify corrupted predictions using the linguistic resources. TransLIST also provides a significant boost with the average 7.2 points absolute gain. We showcased fine-grained analysis on TransLIST inner working. Our code and dataset is publicly available at this link. And in future, we would like to explore the multitasking approach, multitasking with the morphological tagging. Thank you very much.